In section 1.1, where it's really a review of Algebra 2, we're going to review identifying the domain and range of a function, and we're also going to use function notation, as well as learn a little more, review a little more about the real number system. So here we have real numbers, integers, whole numbers, and natural numbers. And let's see, you're not viewing my whole page here, so let me go back. Okay. All right, so we've got a little problem here. Okay, so let's start classifying these numbers. So first of all, real numbers. We'll take -3. -3 is a real number. -3 is also an integer. Is -3 a whole number? No, the answer to that question is no. Whole numbers is a set of numbers that includes the wholly number, which is 0, the one with the hole in it, and then the counting numbers on top of that, which is the natural number. So -3 is not a whole number. -3 is not a natural number. -3 is, however, a rational number, which is a number that can be written as a fraction. Any whole number, any integer can be written as a fraction just by saying, for instance, -3/5. And an irrational number, -3, is not an irrational number, because an irrational number is a number that cannot be written as a fraction, so a non-terminating, non-repeating decimal. Okay, so let's move on to 1. 1 is a real number. 1 is an integer. 1 is a whole number. And 1 is a natural number. 1 is a rational number. And 1 is not an irrational number. Okay, then we have 2/5. And if we think about the number 2/5, so it is a real number, but it's not going to get classified as several of these, which includes the integers, the whole numbers, and the natural numbers. It is, however, a rational number. It can be written as a fraction, and it is not an irrational number because it's not a non-terminating, non-repeating decimal. The number 0 is a real number. It is an integer. It is a whole number. It is not a natural number. It is a rational number. 0 over any number is 0. And it is not an irrational number. And then that leaves us with pi. Pi is a non-terminating decimal. And I know most of you have probably seen the extension of pi. So pi is our only irrational number. So if we take a look at that, here, let's say this is our set of real numbers, everything that we talked about so far. If you notice, you go back and you look at this, everything, all of the numbers there, -3, 1, 2/5, 0, and pi, I should have put here also. All of those are real numbers, okay? So if we think about, how can we classify the real numbers, then what it comes down to is something like this. You've got all of your irrational numbers here. Okay, and then over here on this other side, we have at the top of the list is your rational numbers. Now inside the rational numbers, we have a set of integers, which is the next biggest group. And then inside the integers, we have a special set called the whole numbers. And then inside the whole numbers, we have another set called the natural. So by looking at this diagram, what that means is that if you find something that's a natural number, for example, the number 1, if it falls into this group, then it also falls into all of the other groups outside, except for the irrational there, of course. Now, if you find something that's an integer but not a whole number or a natural number, so for instance, -5, then it goes with everything on the exterior of that, because integers lies within the rationals, but the integers does not necessarily lie within the whole number and the natural. Okay, so that's a quick review of the real numbers. And now let's talk about a few definitions, some things hopefully you remember here. Let's see if I'm going to get a good full screen here. Okay, so a relation is a correspondence between two sets, and most of you have seen an ordered pair, and a relation is an ordered pair, something like this. Your x values and your y values. The domain is a set of all of those input values, or all of your x values. Your range, on the other hand, is your y values. So those are your output values, and probably shouldn't have that space there. And then we have a function. So a function is a special relation, okay? So first you're a relation, and then after a relation you may or may not be a function. So a function is a relation in which each input corresponds to exactly one output. So I like to think of this as like a bubblegum machine, okay? Let's say I have two bubblegum machines, and each one takes 25 cents, okay? All right, in this bubblegum machine I'm having all red gumballs. Okay, and in this machine I've got several different colors of gumballs. Okay, and it also takes a quarter. Now, number one here, if I input my quarter, in every case I always get out a red gumball. So you input your 25 cents and you're going to get out a red gumball. So in this case, what we have going on here is that each input corresponds to exactly one output. You input the 25 cents, you get your red gumball. All right, in this second situation here, I input 25 cents, and I might get out a blue gumball. Or I input 25 cents, and I might get out a red gumball. Or I input 25 cents, and I might get out a green gumball. So you've got several different situations. The fact that you had to say or, you input the 25 cents, I get a blue or a red or a green, that makes this relation not a function. So to clarify things, this one is a function, this one is not a function. Okay, and that'll help you think about it when you start looking at the numbers and you know, you're asked if a certain relation is a function. So let's talk about function notation. Most of us at this time have seen something like this f of a here, and what that means is it describes the output of the function f produced by an input of a. So f is the name of our function in this case. So f is the name of the function. And then we have our x here, which is our input value. That comes from your domain. All right. And then we have all of this other stuff, this 2x plus 3, which involves your input, your x. But you can think of this as the directions that tell you what to do with the input x in order to acquire that output f of x. So let me write that down for you. So okay, so again, the directions that tell you what to do with the input x to acquire the output f of x. And you will see that function notation quite a bit. All right, here we have an example. This is just a set, and it's some values here. So the table below shows the height and arm span of 12 members of a cheerleading squad. And what we want to do is to write the table as a relation and indicate the domain and the range. Well, right now all we're going to worry about doing is just talking about what the domain and the range is. It doesn't really tell us what the input and the output is here. We're just going to assume that it's usually written, whereas this is our domain, is usually either on the left or on the top, and this is usually our range, okay? And when you go to write this as a relation, it would be just the set of ordered pairs. So you could say, you know, 178 is paired with 180. Okay, so you have that ordered pair, and then you have another ordered pair, which would be the 189 is paired with the 180. Okay, so in this case, you already know that this is not going to be a function, because if you input 178, you get 180. If you input I'm sorry, this would be. It's okay to repeat in the range, and I'll get to an example of that in a minute so I don't confuse you. But let's see if we can find, do we have any repeats in the domain? Doesn't look like we do, so we're probably fine there as far as being. So this, if you continue this process, then you come up with your relation, okay, writing it as a relation. Okay, here we have an example that we have in a relation, and we are going to state the domain and the range and then create a scatter plot. And we're just going to do a sketch of the scatter plot and find the rule for the first coordinate. We're going to find the rule for this. So you can see I already have the rule over there for you, but I'm going to give you an idea about how to do this. So the domain, the set of all numbers in the domain, again, really easy, is going to be your 0. And if they're repeated, you don't need to write it. You only need to write it one time. So you've got a +1, you've got a -1, a 2, a 3, a -3. Okay, so those values came from being, all of my input values. Okay, so, and then the set of your range is going to be all of those y values. So that would be 2, and then 2 is repeated, but we don't need to write it again. So then we have 5, 10, and then 10 is repeated, so we only need to have 3 values there for a range. Now, when it asks us to create a, let me put that back, scatter plot here, just going to sketch a little graph of this and then talk about how we would find this. So let's say we have something like this. Here's my coordinate plane, and I go to plot these points. So if I plot 0, 1 is, let's say, somewhere around here, and then I've got the point 1, 2, so that's 1 up 2, and then -1, 2 would be here. This is not supposed to be a point right here, so let's erase that, fix this. Then we have the point 2, 5, so 2, 5 is going to be somewhere in there, and then we've got 3, 10, and -310. So here you can sort of see that this is probably going to be quadratic. You recognize the shape of the graph, the parabola, it's pointing up, so that you know that your leading coefficient for your leading coefficient is going to be positive there. And you notice that this here is one above the x-axis, meaning that's going to take care of this piece here. So that helps you find the equation for that. We'll talk more about finding those equations a little bit later. Okay, in each one of these, we're going to look at the set, determine whether it's a function or not, and tell why if it's not a function. So the first one, and the first one that we have, we can go ahead and conclude that it is not a function, because what you're looking for is repeats in your x value when it's like this. And you notice right here we have an issue. If you input a 2, you might get a 4, or you might get a -1. So this one is not a function. Okay? It is a relation though. All right, and then in B, we're looking again for the repeats. So we've got a 0, a 1, -1, 2, -2, 3, and -3. There are no repeats there. It does not matter. You notice that you do have some repeats in your range or in your y values, but that's fine. That doesn't matter at all. No repeats in our domain, so yes, this one is a function. Okay, and again, let's look at C. We've got 0, 1, -1, 2, 3, and -4. There are no repeats in our domain, so this one, again, is a function. All right, the next thing we're going to talk about is interval notation. An interval is a set of all numbers lying between two fixed numbers, and the following, this chart right here is going to give you some hints about how to do interval notation. Now this looks a lot more complicated than what it really is. If you have trouble doing it the way I'm going to suggest, then maybe we need to go back and look at the details of this chart. But let's just say that let's just say we remember a couple of things, okay? And we are going to, let's add a page and say, we're going to add a couple of things to this. All right, so if you have a parenthesis, you are going to use a parenthesis when the number that we're talking about is not included. Okay, so let's say all numbers greater than 4. In that case, 4 is not included. Whereas if I say all numbers greater than or equal to 4, 4 would be included, and so we would use a bracket. So we're going to use a bracket when the number is included. Okay. Now, we also need to know that you have these signs like greater than or equal to. If it does not contain the equals, then you use the parenthesis, because in that case it's not included. But you might have the equals on it, and it doesn't matter whether it's greater or less than, but if it has the equals on it, then you use the bracket because it is included. And then the other thing that you need to remember, in this case, there are two other things really. Let's say there are two other things you need to remember. The first one is that you are always, let's see if I can spell always correctly. Always use, and that's a parenthesis with positive or negative infinity. So anytime you're talking about something going to infinity, never ending, you're going to use a parenthesis and not the bracket. And then the other thing that you want to remember is, well, let's just save the other thing for now. Let's just say that you use the parenthesis when you're going with positive or negative infinity, and we'll get to the other piece here in just a few minutes. Okay, so we have a couple of examples. The first one is all numbers less than or equal to -4. So if you're talking about the first example, all numbers less than or equal to -4, that can be rewritten as this. Okay, now on a number line, that looks like, here's my number line, here's -4, and I'm going to use a solid circle and shade to the left. Okay, so that's a number line for it. And if I want to write this in interval notation, then, and this is where I'm going to add, you've got to figure out what in this case you only have one number. So I'm going to go back and we're going to add this other thing that I was talking about here. When you do interval notation, what you're doing is you're using some form of this. It's like an ordered pair, like going from one number to the other. So when you use interval notation, you're always going to put the small number on the left, and then you're going to put the large number on the right side. So, and this doesn't have to be bracket on the right and parenthesis on the left. That's just, an example here. So now that we know small number on the left, large number on the right, then we can go back to our example over here and decide what we need to do. So what's the smallest number that could be included here? Well, I'm not sure. I mean, it continues going. You see, it continues. So that means that it's going to infinity. Is that positive or negative infinity? It's negative infinity. That's the smallest number. And the largest it's going to get, so the furthest right it's going to go, is to -4. Now we've just got to decide brackets or parentheses. We know that we always use a parenthesis with infinity, and our 4 is a solid circle. It includes 4, so we're going to use a bracket on this side. So that is interval notation for A. Okay. All right. Now B, this one, all numbers between -7 and 10, including -7, but not -10. Okay. So let's resort to using the number line until we get really good at this. The smallest number there is that should be a negative there. So this should be, it's going from -7 from -7 to -10. Okay, so it's going to include -7, but is not going to include 10. So we have an open circle. All right, so that means that when we go to write our interval notation, it is going to be a parenthesis. It's going from -10 up to -7, including -7, but not including -10. All right. Okay, so we have those two. Let's do the others. All right, so C. So this one is written so that you have your small number on the left. So what we have for C is you've got -3, less than, no equals on that one, less than X, less than or equal to 3. Okay, so in this case what we have is we have it written in a really nice form because we know X the way we read this is that x is between -3 and 3, including 3 but not including -3. So we can go directly from here. We know our small number is -3, our large number is 3. We've got no equals on this part, so I use a parenthesis, and equals on this other part here, so I use a bracket, and that is my interval notation. Okay, and then for D, okay, for D we've got x is less than -3. Again, really easy to work with, but certainly use a number line if you need to. What is the smallest number? The smallest number is going to be -infinity. If you can't see that, use a number line and you'll notice. And it's going to go up to -3. It does not include -3, and we always use a parenthesis with infinity. Okay, so we have those two. The next one is a little more involved, but definitely not hard. So on E, we have -4 less than or equal to x, which is less than 3, or x is greater than or equal to 8. So in this case, I'm going to start out by doing a number line for each one of them, just to make sure we understand. So we're going from -4 up to 3. It includes -4, but does not include 3. And then here we're at 8, and we are going to shade to the right, and it includes 8. So we have this. So I'm going to go ahead, use my OR here. So I'm going from -4 up to 3. I include -4, but not 3. And then I'm going from 8 to positive infinity, including 8, not including positive infinity, or always using a parenthesis with infinity. Okay, so that takes care of our interval notation. And the next example, what we're going to do is find the output for a certain input, and we are going to, so you would just look at your table here and find this. So we're going to find the output, we're going to find inputs, we're going to find domain and range in these cases. Okay, so we start out by finding the output for the input 3. So if I look at where x equals 3, then I notice that x equals 3 about right here. So a lot of times you would think, okay, I look at this point. This is a point 3, and I'm actually not sure what that point is, so I'm going to make one up. It's positive here. Let's say that's a point 3.4. It's actually less than 4, so I'm going to say it's 3.3. Okay, that's a point 3.3. So when you're answering A, you might want to say that f of 3 is equal to 3. Okay, but that's actually not right, okay, because what you notice is that you have a hole in your graph, and then down here that hole gets filled. So when you go to look at f of 3, it's actually where it's filled in, which is down here, and I'm not sure what this is. I'm going to say it's -2. So in this case, if it's not -2 on your graph, then so f of, not -2, but f of 3 is not 3, but f of 3 is actually right here, which is going to give us that f of 3 is -2. Okay? Most of the others are straightforward. It's just that it's just a little complicated when you notice you have a hole in your graph. In some cases, let's say we didn't have this point down here, we didn't have this point, then you would just say it's undefined. Okay, part B asks us to find inputs whose output is 0. So the input whose outputs are 0, I'm actually just going to mark these on my graph, because I'm not sure what those values are. So the input whose outputs are 0 are going to be here and here. So I'm going to say at A and B. So I'm just going to, all right, so that looks, you know, a positive and a negative one, and it definitely looks greater than 3, so maybe it's something like 4. And then the next thing I'm asked to do is to find the y value that corresponds to x equals 1. So if I want to do x equals 1, somewhere there, so I'll look to see where it hits the graph. And let's mark that on our graph, and I'm going to say the y value that corresponds there, and we know it's probably going to be a little bit less than 4 here. Okay, so we just find the y value. I'm going to mark that as C. And then for D, state the domain and range of the function. Okay, this is where it gets um, a little more involved. Let me see how many of these I have. Okay, let's. Okay. Okay, so if I'm doing or I'm taking care of the domain here, then the domain is a set of your x values, all right? So when you're looking at your x values, you know that you go from left to right. So let's go ahead and figure out how far left I go. And I don't have any markings on here, so we're going to make up a number here. We're going to say that's at -4. That's as far as we go to the left, I'm sorry. And then how far right do we go? Well, it looks like we go to 4 on the right. And you know, if you're given a graph and these points are plotted, you can figure out exactly what those are. And then you have to consider there should be a point here. So that's filled in. Okay, then you have to say, do you have any holes? And if not, are those holes replaced? So if we put that blue spot in there, and actually I should probably make it red because that's what the graph is. If I put that red spot, then that hole is replaced and I don't need to worry about the hole. And we're not going to worry about it this time because it's replaced here. So it's okay that we have a hole there, no break in the graph because it's replaced down here. So we go the furthest left we go is -4, the furthest right is +4. All the holes are replaced at this point. So when we start talking about our domain, we need this information here. So we go between these two with no breaks. So that means that my domain in interval notation is going to be from -4 up to 4. Okay, and now let's talk about our range. Now range, we're talking about our y value, so we're going up and down. How far down do I go and how far up? So again, I'm going to replace this point. This is a point that you should have on your graph that's not there. So how far up do I go? Well, the furthest up I go is here. And we're going to say that's at 4. All right. And then the furthest down I go is here, and we're going to call that -5. So I'm going between -5 and 4 with holes. You have a hole here, but it gets replaced here at this height. So that's fine. We don't have any hole. We don't have a hole at that height because if you look at this height here, yeah, we have a hole here, but it's matched here, so have no holes there. So when we're looking at the range, and we want to write our range in interval notation, we put the small number on the left. We go from -5 up to +4, and it includes both of those numbers. Okay, I'm going to try just a couple more of those because those get a little bit tricky. So again, for this one, what we're going to do is find the domain of this one. So we're looking at our horizontal numbers. So what happens on this one? It looks like this we should have. This should be extended to right here. So let's do this, okay? So remember, domain is horizontal, so the furthest left I go is going to be here, and I can count that. This is what I mean. So 1, 2, 3, 6, 7, that's at -7. And the furthest right I go, you notice you have an arrow here, so that means it's going to go to infinity. So I'm going from here to infinity. Okay, and I just have to figure out what's going on in between here and infinity. All right, so I'm going fine. Do I have any holes? Yes, I have a hole, but it gets replaced right here, so I'm okay. I don't need to note that hole. Then I have another hole, which happens here, and I do need to make a note of that hole, and that happens at +3. So that means now that I have enough information to go ahead with my interval notation. So I go from -7, including it, up to 3, not including 3, and then I start back up at 3 and go to positive infinity. Okay, so that's my domain and interval notation there. Okay, now let's take a look at the range. Okay, so the range is my y values here. This is just going to be a point here. All right, so how far am I going up and down? Well, you might think, or you might start out thinking that your highest point is here on your graph at 4. But actually it's not, because if we were to extend this, it's going to continue going forever. So what actually happens is that the highest point on my graph is not 4. It's going to go to infinity. So I'm going to infinity. All right, and then the lowest point on my graph, and I don't have an arrow going that way, it looks like it's going to be at here, which is at -4. Okay, and we have a hole here, but you notice all across here I have that same height of 4, so I don't need to make note of that hole. It is a solid circle, and so I go down here. Now I need to take note of any other holes that I might have. I have a hole here, but as this arrow continues, that height is going to get replaced here. So I don't need to worry about that hole. And so that means that my range is actually going to be pretty easy. I'm going from -4, which is my smallest, including -4, up to positive infinity. Okay, and that's my range here. And then the last set of problems I have is just finding different, given a function and finding different values for the inputs given. So the first one, I'm asked to find g of √2. And this is just a matter of replacing your x's with the √2. So I have x squared plus 2x plus 1. So that means the x is going to be placed with the √2 squared plus 2 √2 plus 1. And now I can just simplify this. If I square √2, I get 2. 2 times √2 is 2 √2 plus 1. And then 2 plus 1 is 3 plus 2 √2. And that's it here. Okay, now for B, this one I'm finding g of 3. And so again, I'm going to replace my x's with 3. And when I simplify that, I get 9 plus 6 plus 1 is going to give me 16. All right, and so it's that. And then for C, this one I'm finding g of r. So if I'm finding g of r, then it's just replacing all the x's with r. And that's all we can do for that one. Okay, and then the last one, D, let's give ourselves a little more space for that one. So we're finding g of a plus 2. That means all of my x's need to be replaced with a plus 2's. And then I need to do a little algebra for that. So if I do a plus 2 quantity squared, then that's going to produce a squared plus 4a plus 4. You can also write that out as a plus 2 times a plus 2 and do your FOILing process if you don't know the shortcut. Here I distribute the 2 and I get 2a plus 4 plus 1. And then I end up with a squared, combine my like terms, plus 6a, and then plus 9. Okay, and this is what I end up with here. Okay, so that's all I have for section 1.1, and we'll continue on with 1.4 next time.